Hey everyone, welcome. In this video I would like to give you an overview of a couple of tools I've been working on for the past few weeks, and although the project is still not quite finished yet, I believe there are already some potentially useful information that I could share. Everything you see here is much more of a proof of concept than anything else. I am not affirming that these methods that I developed are the best option, because I'm sure some things could have been solved through different and even more optimized solutions, especially the way that I handle the creation of new geometry every time an action is performed. But regardless, I think there are a few interesting things that could help someone. So without further ado, let's jump right into it. We start off with a tool that generates a grid for us to work on. And this is simple, very simple network. We start off with a simple circle, and this basically uses the instant meshes SOP, which creates a quad mesh from the input. It could have been a different input as well. Just to demonstrate, we could have a hexagon, for example, or anything really, that as long as we have a quad mesh, because everything depends on that every primitive has 4 sides. Previously the tool only accepted flat incoming geometries, like a flat grid in this case, but after a while I wanted to try to implement something that worked with any input, like a mountainous shape such as this one. So I had to change a few things for that to work, and I'll show you that in a second. And the way this works is it uses the Python states in Houdini. They were introduced a few versions ago. And how this works is this is an HDA, which has this tab here called interactive, and this can have Python code, which will create a Python state in the viewport for us. And I'll go through this in a bit more detail in a second. I just want to show you first how it works. So let's forget this for a second. This is where we generate the little town here, a favela or a slum in English, based on the output of this tool, which I very cleverly chose to call it Click-Extrude Tool, although it doesn't extrude at all. It doesn't use the extrude node, and I'll get to that why. But basically this tool works like this. If we press enter in the viewport in here, you are inside the Python state. So if I perform a click or click and drag, new boxes will be created in that location, and I can do that indefinitely, create boxes on top of each other. I can make overhangs like this. And another functionality that I implemented was to hold Control and to enable the user to undo a certain step instead of pressing Ctrl Z, which would also work, but it's a bit fiddly. You had to press it a bunch of times for it to actually undo what you wanted to. So you just basically click holding Ctrl and it will undo that action, or better, it will delete that box. And this is pretty much what this tool does. It uses the Python viewer state to shoot down a ray from the mouse pointer. It will select that primitive. Based on the primitive number, I will then select that face, and then using a adaptive grid, I will use that box from that location, and then it will be stashed, and then this creates a loop where every time I use the tool, this geometry gets stashed. So the next iteration that I used, it's using the geometry that has the new geometry created upon it. So a couple other things in here. If I press reset, this is going to basically delete everything. It's going to reset the stash. It will get this incoming grid and it's going to stash it back as the incoming geometry. And there's also in here the generate random function, which will basically, using these digits here, create, for example, 128 boxes. And if I keep pressing this, they will just keep popping up. turn this off so we can see. And in theory, this could still work. This would create a little town for us if I use this other tool. But since this is a very chaotic thing, a few of the things that I created, like the streets and all of that, they don't have connections to each other, but you could still use this as a base, and you could start, for example, customizing it a little bit, creating pathways and so on, so you could create a more full scene in pretty much no time. So this speeds up the things a little bit. Sometimes I will just generate a seed and then go from there. As you can see, there are not many variations still implemented. Like the roofs, there are only 2 types of roofings, and these doors are just dummies, and windows are not even windows yet, just placeholders really. But as you can see, really fast you get a few interesting results for a variety of things. So going back to the Click-Extrude tool, we'll start to look right now inside of it, how it works. Let's start here maybe with these 4 boxes in, for example, and jump in. We get the input grid in here, which is always what we create on the upper tool here in the squad grid generator. It gets fed into here. So whenever an action is performed, this network cooks, right? The information gets passed down. So whatever is on the stash geo gets put into the stash in here. So this stash here right now, since the network just cooked, this switch is basically checking if this here has a number of points greater than 0, then we choose this input instead of the clean geometry. So just a simple way of choosing this input instead of the other one in case this one has a geometry. So I want to show you first this network here, so you can understand how the selection of the geometry works, and later I will show you how the Python code works to send information to this network. So the Python is going to generate a string of selected primitives, which is, if we forget about the code for a while, that's pretty much straightforward. You're just basically clicking and selecting primitives in the viewport, and they get fed into this Rango in here. So in this Rango, I do a little bit of cleanup and so on. But the most important thing is that this grid here, the original grid, is being fed into this little network here called adaptive grid. Why do I call it adaptive, right? We have here a way of checking how many floors or how many boxes were stacked on top of each other. So right now we're at level 1, and the floor number here, if we check the detail attribute, it's going to be 0 because this is the first floor. So that gives us that this grid should have only this amount of levels. So the way I did it was that this will always have 1 extra grid on top of the maximum height, like so. Like I told you in the beginning, we're not using extrude in here because it cannot be compiled yet. I hope they implement it sometime in the future. But basically, it's just a trick of transforming it up and skinning it and generating groups of extrude back, side, and extrude front, just like the extrude node would do. And we do that for every single cell. And I also generate what I call directional points in here, which are just basically points on every face of each cell, which I can use for when this primitive on the bottom here is selected, I can check if this cell was selected or not using these points. So let me show you an example now that you've seen how the grid works. This grid is also fed into this loop. So let's imagine here I have this, my first iteration of the tool. My first attempt at creating geometry were these 4 boxes, and now I want to select box, or rather the primitive 1, 3, 4. Let's do that one, for example. Let's do it manually so we can inspect and understand. Let's imagine this here is being set by the Python code. Here is being fed 1, 3, 4. So in here, let's blast 134 non-selected. So let's imagine this is my selection from the tool. So having this selected primitive here, let's feed it into to our loop like so. Let's select in here just so it cooks. So how this works is instead of extruding it, the problem with the extrude in this case, this didn't give me the result that I wanted, because whenever I had an overhang, the overhang would just extrude that face according to the primitive normals, right? And I always wanted it to match with the original grid. That's the whole point of it. That's why I created this method, because extrusions were independent of the grid. So that's why I came up with a way of having a pre-constructed grid and selecting them, those cells as needed. So the way this works is rather simple. We just use a little tube which will select those direction points from the construction grid, which have those points in there, as you can see. So basically we create that little tube which will select then the box number. So if we see here, we just basically are checking for a box number which is created in the adaptive grid itself, and this gets passed down. So imagine that this is a selection of multiple primitives, let's say 134 and 117, like so. So now we have two primitives in here. So this works on a for each. This is gonna run for each of those, and then we're gonna get right now, of course, only one of those because it's inside a for each, but both of those boxes will be selected. So this is a very, like I said in the beginning of the video, kind of like a hacky way of doing this, but for smaller scales, this works really fast. I believe that if we had to go on huge scales, like something like this, 1 kilometer wide, this could potentially be slowed down because of the grid. This grid would have to be calculated every time something exceeded the maximum height previously recorded. But for now, I believe it's an okay solution. It works well. So let's now undo what we did here, so we can go back to the original state. So basically we just simulated what the tool does at runtime, and whenever that happens, this gets merged back to the grid that you had previously, and this gets passed to the stash geo node, which is just a reference. And whenever this here gets a new input, it gets stashed up here again, so the loop continues. Whatever happens here in the bottom, this happens after you finished clicking, like you released your mouse. So this basically just prevents the below networks to start cooking or cooking twice while we are at creating the boxes. It just speeds things a little bit because it won't only stash this final step after everything has been finished by the tool. Now let's have a quick look at the Python tool code itself. I won't go too much in depth. I'll just show an overview because I myself am not very experienced in Python yet. This is used rarely by me in Houdini, especially. I'm mostly doing things in Vex, but this was a nice challenge to start coding things in Python as well, to learn as well. So a lot of things here were achieved with help of Simon Verstraete, very nice guy, which has been doing a lot of similar things with Python states. And a lot of this was achieved by studying the documentation in the Houdini webpage. They have a whole section dedicated to Python states in Houdini. So like I said before, this code runs whenever you click enter here in the viewport, and then you are inside the Python state. So everything now you do, or whatever you coded in here, can be used. So if we reset here, let's start from the beginning. In here I just declare a bunch of variables that are useful for me later on. As you could see here, whenever I click enter, you have this little prompt. So this is being defined here, and also being called on enter here. This is when I press enter, so this is calling this function. These functions here are just used for updating the stash geometry, like I showed you before. And the way this works is this HDA has a bunch of parameters in here which were promoted directly from the nodes themselves. So if you lay down a stash node, you see you have a button for stashing, but you also have this here, and this can be dragged into your parameter interface, and that can be used for directly overriding whatever is stashed in there. A very helpful thing, very useful. So this is what I'm just basically declaring in here, that this function should overwrite whatever is stashed here. So we have two stashes, the stash and the final stash. And so whenever we enter this onEnter function and our mouse starts hovering over the scene, we are also calling this function, which is onMouseEvent. And in here we are just simply using this functions, which are, if I'm not mistaken, imported in here. This SU refers to this here, Viewer's Data Utilities, as SU, which has a function called Geometry Intersector, and it takes the geometry as the argument. So with this we can basically fetch whatever primitive the mouse is hovering over. So this is what we do here, and whenever this says it's active, means that my mouse is being clicked and dragged in the viewport. So we are just simply storing that primitive inside this variable, and then here do a little thing that will clean up our input a little bit, because these arrays, if my mouse stays hovering above this this array which I'm appending this prim to, gets huge. Could be potentially a problem. So if I transform this into a set using a list and a set functions here, this gets cleaned up and gets basically rid of all the duplicates. So it speeds up a little bit. So like I mentioned before, this gets written into the groups here. So we have something called extrude prim, which is this here, this parameter called group. In fact, let's take a look at that. I'm just going to accept. I want you guys to pay attention to this. Whenever my mouse is in here, I click and drag. You will see the array gets written over to the parameter with the primitive numbers that I'm clicking on. So let's see that one more time. You see 170, 171, 152, 172. They all get written over to this parameter. So this is what gets passed onto this set targets wrangle in here, right? So this is basically getting that value, and in here, like I said, I do a little bit of X cleanup. I get rid of these brackets and I replace the commas with nothing, so that we have something that the Houdini nodes will understand better. So just basically just the numbers of the primitives, which can be overridden and then passed down to this group expression. This is basically how this is being made. Couple more things, like I mentioned, that if the control key is being pressed down, this will undo. So it happens a very similar process in here, just basically using other attributes and storing them somewhere else, and using that I can actually show you that, because this is a separate network in fact, but a very similar one. But because instead of using a adaptive grid like in this case, we are using the input itself to check. So if I click basically it's the reverse process in here. If I click a cell that already exists I will do the reversed process in order to get rid of that box. This gets handled by this this area of the code here, which will basically do the same thing as the other, just write down a list. And in case the reason changed, which means you stopped pressing with your mouse, things will get basically cooked or baked. Yeah, so one more thing that I did here was to implement these two buttons that I showed you, which are in here. This first one is for the reset, which basically just cleans up all of the strings, all of the arrays that I created before, zero them out, stash like if you set a stash to none, it's just basically gonna wipe it out. So, and then I run the self-update final stash as well function. And then the generate here, this is more of a Python solution for generating a sequence of numbers which go from 0 to the max amount of prims in your incoming geometry. And that's pretty much it. This bottom part here for creating viewer state template is a default thing. Whenever you create a new viewer state, this gets imported automatically, except for these two lines of code, which are necessary to generate the two buttons in there. So this is also in the documentation if you have any doubts or questions. I hope to be able to make this tool available to you. If you have any other questions or suggestions, please let me know. I would want to show you this one now as well, but as you can see, it's still very much of a work in progress. Haven't packed anything yet. There are a bunch of little small tools that help me achieve these results, and I think I will be able, and I hope to be able to show you a more developed or a more finished state of this project in the near future. But for now, I hope you guys enjoyed the overview of the Click-Extrude tool. Let me know if you find this useful. Let me know if you have as well any other suggestions on how to do it differently to improve it somehow. I'm pretty sure if we could create a grid dynamically on the fly, for example, according to the demand of newly selected primitives, the overall performance could be improved quite a bit, especially for larger scenes. But for now, this is what I've been working with. Make sure to follow me on Twitter if you'd like to get some more regular updates on this project and also other things that I've been working on. Thank you for watching, and I'll see you in the next one.